Well, in this video we're going to start to talk about triple integrals, finally. I know you're looking forward to that. But before we do that, let's take a moment and do this warm-up problem. So pause the video, try it out, and resume when you're ready. Okay, well, in case you had a chance to work on it, here is the answer. So, again, you're thinking of this little region, so it's bounded by the x-axis, and then when you graph it, it's bounded by the line y is equal to x, and x is equal to 1. So it's this little triangular region in here, and I'll highlight it to the best of my ability. Okay, so we want to integrate our function over this domain. Okay, and so this is a prior skill. If we do dy dx, again, the first one we want in terms of x, so we're integrating y from 0 to x, and then x from 0 to 1. And then if we switch the order, then x is going to go from, on the left side, y to 1, and then y is going to go from 0 to 1. Okay, and then now if we decide to do it in polar for some reason, we're taking r, and r is actually extending, if we think about it in terms of theta, it's going to extend from 0 to secant of theta, and I encourage you to pause the video and work that one out. And then the angle is going to go from 0 to 2, or pi over 4. Okay, so again, just a little warm-up, but our focus today is going to be on reviewing what we already know. So if we look back at single variable integrals, kind of the process that we used when we were doing single variable integration was, okay, we had, we took this interval, AB, and we split it into n intervals, or subintervals. Okay, and then in the subinterval, we looked at this point xi star, and we really went off from that, and then we did some work with that. So sub interval, okay. All right, and then with that, we kind of did that for any interval, and then we looked at g of xi star, so we found the function value at that point, multiplied by the width of the interval, because presumably all the intervals were the same, and then we took the sum over all possible i's. So that's I is equal to 1 to n g of xi, and then we took a limit of this, and then we assumed it exists. Okay, and then really what we got at the end was integral from a to b of g of x dx. Okay, and so that's your start from Calc 1 that you've heard over and over and over. And then now this year we looked at double integrals as well. And so now we took our region R and split it into n squared subrectangles. Okay, and then we looked at the point xij star in the ij subrectangle. Okay, and then we looked at the function value, so g of xij star, multiplied it by the width of the smaller subrectangular region, and then took the sum over all possible I and j, n, and then we took a limit, and then we end up getting the double integral over region R of g of x, y, dx, dy. And we did a lot of things with this, and we have been doing a lot of things with this. And so then, but the only thing that we had to remember is, okay, well, what if the region wasn't rectangular? This is where that f extension came into came into play, so you might have to review that from the first time when we were in section 5.4. Alright, so then I want to ask the question, well, we've done single variable integrals, we've done double integrals, what about triple integrals? And, well, the story's probably pretty similar, but just as we think about triple integrals conceptually, our domain of integration, okay, when we had one variable, our region was an interval. In 2, we had a two-dimensional region. When we have a triple integral, we should probably have a region or a domain of integration that's a solid. So we're integrating over a cube, something like that. And just also notice that we can't graph because the function, since it takes 3 variables for an input, it would actually be in 4 dimensions. Okay, and then so when we talk about triple integrals, we're going to be on a domain, and then we're going to call the domain a box B. Okay, so in terms of what we're going to do conceptually, it's very, very similar. We're going to break box B into n cubed subboxes, and then we're going to say let xij k star be in the ijkth subbox. And then we're going to look at the function value, x of ijk star, so look at the function at that point, and multiply by delta x, delta y, delta z, and we're going to take the sum over I, j, and k from 1 to n of all those, and then we're going to take a limit, and then we're going to end up with triple integral over box B of g of x, y, z, and then dx, dy, dz. So conceptually, all the integrals we've studied are the same, and so we'll start seeing some of these in the next video.